Hello students, I am Dr. Madhurima Pandey, Assistant Professor in Physics from School of Applied Sciences and Humanities, Haldia Institute of Technology. Today in this lecture, I am going to talk about an introduction on simple harmonic motion. Okay, so when we talk about motion, we can classify the objects around us. Okay, so the objects which are around us that can be classified into two parts. The objects one which are rest with respect to us and the objects which are in motion with respect to us. The particles or objects which are in rest just like a refrigerator, TV, house, etc. And the motions just like a moving car or flying bird. Okay. So in this particular chapter, we are more focused into the objects which are in motion. Next. So you can see that we can classify the motion into two parts. One is non-periodic motion, another one is periodic motion. So first try to understand what is non-periodic motion. Non-periodic motion is a motion that means which motion is not repeated at a particular certain time interval. Suppose you can see there is a block. Okay. So when I push this block, it will change its position from point 1 to point 2. Okay. So this motion is kind of a translatory motion. So it translates from one point to another point. But its motion is not repetitive in nature. Okay. So that kind of that kind of motion is called non-periodic motion. So the motion in which the body moves from one place to another place with respect to time, and it is one kind of a non-periodic motion, just like a moving bus, a flying aeroplane, okay, a moving football. Its motion is not repetitive in manner. Another one is a periodic motion. What is the meaning of a periodic motion? Periodic motion means the motion which repeats itself after a certain interval of time. Just like you can see, here is a pendulum. So this is the pendulum, this is the equilibrium position, that is when the particle is in the rest positions. Okay. And when we disturbed this pendulum from its rest position, it will move like this. Okay. So suppose we displace the pendulum from at the positions 1. Okay. So when we release it will go to this directions and again come back to position 1. And again it go to this positions and again it come back to position 1. So that means it changes its positions after a certain interval of time. So if the motion of a system repeats itself after a certain interval of time, then that motion is called periodic motion. Just like the motion of a simple pendulum. Also, in our childhood, we play that we tie a stone in a rope and we just rotate like this. That motion is also a periodic motion. Also, the motions or vibrations of a spring system, that is also under the category of periodic motion. So now next. So now we are more looking into the periodic motion. So we can classify the periodic motion into two parts. One is oscillation and another one is non-oscillatory motion. So let us try to understand what is oscillation. So first, take again the pendulum 1. This is the pendulum and this position is the mean positions, or rather we can say equilibrium position. That means there is no disturbances. So when we change its positions from its mean to the positions 1, then what happens? It will go back again in these positions. Again it will go back to positions 1, again in this position. So you can see the motion is itself around the back and forth around its equilibrium positions, right? That it is moving this left direction and the right, left and right. So that means there is a back and forth motion around the equilibrium positions. This type of motion is called oscillation. I am giving you another one example. So this is a block which is attached to a horizontal spring. Now this position is this position. It is its equilibrium positions. So when we displace this box from its equilibrium positions, suppose in these directions, because of this spring, it will just oscillate. So when it oscillates, it will oscillate like this, in these directions, again these directions, again these directions. So you can see the nature of this motion is around its equilibrium positions, the back and forth. Okay. So this type of motion is called oscillations. From this definition, you can also see that if a body in periodic motion moves back and forth along the same path around its mean position, then the motion is called oscillation. Now looking to non-oscillatory motions. Non-oscillatory motions, there is a periodic in nature, but there is not like a back and forth. So if you see that when we tie any stone with a rope and you just rotate like this, so you can see this will take a full motion. Again, it will take a full motion. So though it is a periodic, but it is not like the motion is not like a back and forth of its equilibrium position. First of all, there is no like a equilibrium fixed position. Okay. So the motion is not in nature that it is a back and forth around this equilibrium position. It is a periodic in nature, but not a back and forth motion. So that means that is called non-oscillatory motion. Okay. Okay. Achha. There is another term which is very important, that is vibration. Vibration and oscillation, there is no particular technical difference. But when we can use this term vibrations, that when the frequency is very high, then we can call oscillations as a vibrations. I'm giving you one example. You can see there is a guitar string. So when we plug in any guitar string, you can see that it is vibrating very fast. Very fast means that its frequency is very fast. So that means we can't see the vibrations in our open eyes. That is totally just like invisible to us. So that means this is oscillations, but their frequency is very high. So when we are considering any system where frequency of the oscillation is very high, then we call them as a vibration. There is no rather technical difference. We always call vibrating the guitar string or vibrating or any string instrument. Okay. So in that particular cases, we use the term vibrations. Otherwise, it is same oscillations. When you use the frequency, the frequency of the oscillation is very high for a particular system, we call it as a vibration. Next. So now let us try to understand what is simple harmonic motion. So when we can call oscillation as a simple harmonic motion, or in short SHM, that when the amplitude of oscillation is very small. Let us consider. This is let us take a simple pendulum, and so this is its mean position. That means there is no disturbance. So now we just change its position. Now, how this change happens? This change happens in the angle. Right? But let us consider this is theta. So when this angular displacement is very small, that is less than 10 degree, then we can call the oscillation is simple harmonic motion in nature. Also, I give you the definition. What is the simple harmonic motion? First, I read out then I try to understand what is simple harmonic motion. It is a periodic back and forth motion produced by a restoring force that is directly proportional to the displacement and in the opposite directions. There is many terms which is unknown to you. First one is the known, that is I have already discussed what is back and forth motion. Back and forth motion means the motion which is around its equilibrium position, which is produced by a restoring force. Now we have to understand what is restoring force. So restore, what is the meaning of restore? Restore means that we try to restore our original position. Suppose this is my original position. When I move like this way and again come back this way, that means I try to restore my original position. So here is also there is a force named as restoring force. That means a force which is acting on a particular system to bring back that system to its original position. Okay. And that restoring force will be directly proportional to the displacement and in the opposite direction. Let us try to understand. See, this is a spring system. Okay. This is a spring system. Now, when you can see, this is the direction x. Okay. This is the x directions, one-dimensional x directions. So when there is no disturbances, so then the particle or the box are situated at a position like this positions. Okay, you can see there is a 0. So that means there is no displacement. So now when you displace this in or this mass into these directions, suppose the displacement x equals to a. So then what happens? We disturb its position. So because of this restoring force, this particle will try to come back to its original position. Okay, so this is called the restoring force, the force which is applied on a particular object to bring back the system into its original position. Okay, so now you can also see that when we displace it in the positive direction, the restoring force is in the opposite direction. That is also mentioned here. That is, the restoring force is directly proportional to the displacement and it will be in the opposite direction. Okay, in the next slide also you can get a clear picture. So from the simple harmonic definition we get one definition, that is what is restoring force, that is proportional to its displacement. Okay, so what I mentioned, that if restoring force is proportional to displacement. Okay, so when there is a proportional term and when we try to avoid this proportional term and try to see the equal sign, so then what we do? We incorporate a constant. What is this K? This K is called spring constant. And as the definitions from the simple harmonic motion, this force should be in opposite directions of the displacement. That's why here a minus sign appears. So then this minus sign indicates that the force and the displacement, they are in the opposite directions. And this law is a very popular law, that is called Hooke's law. Okay, Hooke's law. Okay. So in this slide, I try to jot down that how Hooke's law applied to a spring mass system. So you can see that this is the positions when x equals to 0, that means at its equilibrium position. So there is no restoring force, you can see f is equals to 0. So now when x is displaced in its positive directions, then you can see f is the negative. Why f negative? Because if x is in this direction we displaced, then according to the definitions, we know that the force will be in the opposite directions. As well as in this case, you can see we displace the particle in this left directions, so that means the force will be in the opposite directions. So that's how Hooke's law applied to a spring mass system. So you can see force is equal to minus kx. This minus sign indicates the opposite directions of the force and the displacement. So these are some conditions for simple harmonic motion. The first and foremost important one, that motion should be periodic as well as oscillatory. The second one is that the restoring force term, that is the restoring force acting on the particle which is proportional to its displacement and its direction is opposite to the directions of the displacement. The third one is the system should have some inertia, and the fourth one is that the system should be frictionless. Why? Because if the friction is present, then there an additional frictional force term will appear in the system. So that is unwanted here. So that's why the system should be frictionless. So these are some conditions for simple harmonic motion. Next, in this slide, I try to give some examples of simple harmonic motion. It is a very interesting one. So you can see this is a simple pendulum, and there is a 3 positions. Positions 1, position 2, and position 3. What are these positions? Position 2 is the equilibrium position. That means the pendulum is at a rest position. There is no displacement. What is 1 and 3? 1 and 3 are the position where we give the maximum displacement. Okay? Achha. We neglect here the mass of this rope. We neglect the mass of the rope, as well as we consider that there is no friction. Okay? So when we displace the simple pendulum, then its motion will be simple harmonic motion. Okay. So now when we talk about a motion, so then we have to consider some equations. Otherwise we cannot calculate that motion theoretically, right? So we need some equation of motion. So let us try to understand how we can calculate the equation of motion for this particular system. So you can see here we displace the bob or displace this pendulum in these positions. Now, what is this angular displacement? Angular displacement is theta. Okay. So now how many forces acting on this bob? That is our point to be concerned. First one is the very common one, that is the force due to gravity. Okay. So that is F equals to mg. What is g? G is the gravity accelerations. So F equals to mg and m is the mass of that bob, this bob. Okay. So F equals to mg, that means force due to gravity, and that will be in these directions. Okay. And another force is the force due to the tensions of the rope, right? And that is acted in these directions, Fd. Okay. So now from the mathematical concept, you all know that when this angle is theta, so then that angle will be also theta. So that means there is two components of this gravitational force mg. One component where the theta is according component versus the cosine component, that is mg cos theta. This one is mg cos theta. Okay, and this one will be mg sin theta. So we get two components of this gravitational force. Now you can see this mg cos theta and this tensional force, they are opposite to each other and they are equal in magnitude. So that means from this condition we can cancel out these two forces, right? They are equal and as well as they are opposite to each other. So which force is only left in our hand? That is only the mg sin theta. So because of this mg sin theta forces, this swing happens, right? That means when we displace the bob or displace the pendulum, it will swing like this. That swing happens when because of this mg sin theta force. Okay. So now from the Hooke's law, we know that force should be equals to minus of mg sin theta, right? Because the displacement and this restoring force, because we displaced that in, we displaced this bob in these directions and the swing happens in these directions. So that means the force and displacement, they are opposite to each other. So where we can call F equals to minus mg sin theta. This minus indicates that the force and displacement are opposite to each other. Now, if you remember, I mentioned that we can call oscillation as a simple harmonic motion if its theta is very small. So theta will be very small. If theta is very small, then we can assume that this sin theta equals to theta. Okay. So from in the next slide, okay. So from here we can write F equals to minus mg theta. Okay. Now what is this theta? This theta is basically x by L. How it happens? So let us draw here. So this is our pendulum and this is the length of the pendulum L, and the displacement happens is x, and this is the theta. Okay. So now if we consider sin theta from this triangle, then what would be the sin theta? That sin theta will be x by L, right? Perpendicular by the hypotenuse. Okay. So now the theta is very small. So from here we can write theta equals to x by L, right? So from here we write theta equals to x by L. So what will be x? X equals to theta L. So now in these expressions, F equals to minus mg theta, just we replace theta as x by L. Now what is F? Force. Force is basically from Newton's second law, we know that it is mass into accelerations. So F is basically equals to ma, that is mass into acceleration, equals to this one, that is minus mg by L. Now what is accelerations? Acceleration is a basically second order derivative, or rather first order derivative velocity with respect to time. And if we express that in terms of displacement, it will be second order derivative of displacement with respect to time. So here we write m d2x dt2 equals to minus mgx by L. Now on the both side there is a m, so we can cancel out both m. So from here we get d2x dt2 equals to minus d by Lx. So d2x dt2 equals to plus d by Lx equals to 0. So now what is this d by L? This d by L is considered as omega square. So omega square equals to g by L. Now what is omega? Omega is called angular frequency. Okay. So what will be omega? Omega will be root over g by L. Now how this angular frequency relates with the normal frequency? That is equals to 2 pi into frequency. This is a very important equations you need to remember. So omega equals to 2 pi into normal frequency. So what will be the normal frequency? F will be omega by 2 pi. Now we know omega root over g by L for the particular this simple pendulum system. So it will be 1 by 2 pi root over g by L. Okay. Next, we have taken another examples that is mass at a spring, and we know that it is a very easy one. The F equals to minus kx, which I already discussed. And what is this F? This F we can get ma, that is mass into accelerations. And if you put all the values in the left hand side, we will get again this type of expression, d2x dt2 plus omega square x equals to 0. So this is the equation motion for simple harmonic motion. Okay, so and for this spring system, what is this omega angular frequency? That is omega equals to root over k by m, where k is the spring constant, m is the mass of that particular block. So if there is an equation of motion, that means there should be some solution. So the solutions of this equation of motion will be x equals to 8 cos omega t plus delta, and cosine function, that means this is the nature of a sinusoidal function. So now later I will try to understand what is this particular parameter. Okay, so this is the solution, okay, of this equation of motion. So in this slide I have just for your good understanding, I have just short out what is the particular thing, that this is the equation of motion and this is the solutions for the case of particular simple harmonic motion. If we take a simple pendulum, then this is omega equals to root over t by L is the angular frequency, and for when we take a spring system, it will be root over k by m. So that means you can see that angular frequency is not a universal thing. It depends on the system, which type of system you are considering. Depending on that, we get the different values of omega. Okay, so now let us try to understand each and every parameter of the solutions. So x is basically displacement. Now what is a? So this is a cosine function. So you can see we have to write it down or draw a cosine function, and this is a displacement versus time graph. Okay, what is this a? This a is basically the displacement, maximum displacement from its mean positions. So when there is no disturbance, it will lie on to this x axis. There is no displacement. So when the displacement happens, okay, this a represent the maximum displacement. So which is called amplitude. Okay. What is the time period? Time period means the time interval in which the motion repeats itself. You can see, if I try to draw here. So at this time, it is the maximum positions, and after a time interval, it is capital T, we again get the same maximum positions. So that means the position itself repeats the same position after a certain interval of time, and that time interval is called time period, which is capital T. Now what is this angular frequency? Okay, so this is omega is called the angular frequency. Angular frequency is basically the number of oscillations per unit time. Okay, so when we take a simple harmonic motion, the motion which is periodic in nature, we name it as an angular frequency. Okay, and this is the relations between angular frequency, which I have already discussed. Okay. You can see there is an animation here. From here you can get that when it rotates in one radian or one cycle, how much angular frequency we get, how much normal frequency we get, that we can get from this animation. Okay. Now what is this delta? This delta defines initial phase. What does the phase means? Phase means it describes its state of motion. That it is at rest position or it is in motion. Okay. Its state described by this delta. So at the initial phase of time, initial phase means when the time t equals to 0. If t equals to 0, if you put the value here t equals to 0, then what we get? X equals to a cos delta. Okay. Now what will be this delta? Delta will be cos inverse x by a. So initial delta means initial phase or epoch. Okay. Next, so if we know the displacement, then easily we can calculate the velocity. So velocity is basically the first order derivative of displacement with respect to time. When we take a derivation of cosine function, that will give you a minus sign, and here is omega coefficient here. So here is a minus omega a sine omega t plus delta. Okay. So now from this equation 1, we can get cos omega t plus delta, that is exactly x by a. So if we know cos omega t plus delta, then we can easily get sin omega t plus delta, because we know cos square x plus sin square x equals to 1. From there we can get. So this is root over 1 minus cos square omega t plus delta. Now this value we already know, that is x by a. Okay. So from here, this is a square, so x square by a square. So if you do more steps, if you go through more steps, we can get what is the value of v. V will be plus minus omega root over a square minus x square. This is a very important expression. Okay. So this is expressions is velocity. Now if we do one more derivative, that means if we take a derivative or differentiate it with respect to t, the velocity, we differentiate velocity with respect to t, we get the acceleration. Okay. So these are the two expressions for velocity and acceleration. So here we get the graphical representations of this displacement as well as velocity and acceleration. Within the same graph, we can get easily the comparison between these three parameters. And when we get the maximum velocity or minimum velocity, or rather maximum accelerations and minimum accelerations, that we can see from here, we know that from this expression, when x equals to 0, x equals to 0 means when it is at mean value, we get v equals to plus minus omega a, because x is 0. And for x is 0, what will be f? If we put here x equals to 0, it will be 0. So, and when x equals to a, that means when it's a maximum displacement value, that means the amplitude. So if you put here x equals to a, you can get v is 0, right? And if you put here f equals to x equals to a here, so the acceleration f will be omega square a. So that's how we can get the maximum value of the velocity and maximum value of the acceleration, or minimum value rather. So now the energy part. So any kind of mechanical energy can be classified into two parts: kinetic energy and potential energy. Now what is this kinetic energy? Kinetic energy means when we talk about any particular object which are in a motion, right? In that case, the energy which we consider, that is called the kinetic energy. We all know the kinetic energy equals to half mv square. Okay. And v, for this particular case, for the case of simple harmonic motion, we already know what is the expression of v. That is v, sorry, that is v equals to omega root over a square minus x square. So plus minus. Okay. So when we put v value here, then we can easily get the value of energy, kinetic energy in simple harmonic motion. Now what is potential energy? Potential energy. Potential energy is the energy stored within a body because of its position or configuration. Now let us I give you one practical example. Okay, you can see this is a rubber. What is a rubber? Rubber band, that is an elastic body, right? So I just keep that like this way. Now this is a piece of a paper. Now I just basically in childhood we do many times this play. Just I try to stretch this rubber band. So that means what happens here? Its configuration of this rubber band changed. So because of that, energy stored within this particular system. So when I release that, you can see, okay, this particular piece of paper will go away. So that means how this happens, because when we change the positions of the configurations of this particular rubber band, there is an energy stored within the system. And because of that energy, when we release that particular paper, it will go away. Okay, this is the concept of the potential energy. So now, this is the conceptual thing. And now, if we try to understand what is this expression, this potential energy EP will be the work done by the force. Now, what is the work done? That is force into displacement. This is a very basic concept. So this minus sign here appear because we consider work is done by the force. If the work is done against the force, then we can consider this is positive sign. So this totally depend on in which frame we are considering. Now, if we already know F equals to minus K x. Okay. So when we put that and when we take the value 0 to x dx, that is a particular integrations, and if you do, it will get half k x square. And what is k? K is basically omega equals to root over k by m. From there, we can get the value of k. So this is the expression we get for potential energy. Now next. So now at which position we get the maximum value of kinetic and maximum value of potential energy, that we try to see, for which first I write down the expressions for kinetic energy. Ek equals to half m omega square minus x square half m omega square a square minus x square, and EP equals to half m omega square x square. Okay, so now you can see when the position at 0, that means at mean positions, if you put x value 0, we get Ek equals to half m omega square x a square. That means at this position. And when x value is a, if we put x value is a, then we get Ek is 0. And as well as you can see, this kinetic energy, which is a functions of x, that is kinetic energy is a x square. It is a functions of the x square. So that means the nature will be, so that is like this. Okay. And when we consider the potential energy, when we put x equals to a, we get at x equals to a, we get the maximum value here, EP. Okay. And when x equals to 0, this equals to 0. Okay. When x equals to 0, this EP is 0. So this part, this is basically giving you the potential energy, and this one is giving you the kinetic energy. Now when we take the total summations of this both kinetic and potential energy, you can see this will give you half m omega square a square, and you can see there is a no particular parameter of x, so that means the energy does not depend on x, so that means we get a constant value. This red line indicates the constant one. So from this slide, we can claim that the total energy of a simple harmonic motion at any instant is constant. It is a very important one. Okay, constant means the total energy is conserved. Okay, total energy is conserved. Okay, and Last part, that we can derive the equation of motion from the conservation of energy as well as. So that from the total energy of the oscillator, that means the kinetic energy plus potential energy, that is a constant one. So now when we differentiate these expressions, we will differentiate with respect to t, you can see that the equation of motion of simple harmonic motion appears. So that is also the one type of question may come, that how can we derive equation of motion from the conservation of energy. From this slide you can get that idea. It's a very easy one. So here is the end of the introductions of the simple harmonic motion part, and the important part is here is that how we calculate the kinetic energy and potential energy part, and there is one type of question may come that show that the total energy of a simple harmonic motion is a constant one. So this is the some important part. So if you have any issues, you can ask me in class. Thank you.